number 2.
Oh, hello. That worked. There we go.
All right.
Okay. You're in charge.
Yeah.
Okay, so yeah, I'm going to talk about the current state of using fundamental QCD tools, in this case lattice QCD, to try and understand something about hadron resonance physics and the kind of stuff that we want to measure in GlueX. And of course, I'm not going to be able to or even try to really explain how the calculation is done in any detail. I just want to show you where the state of the art is, how it's moving forward, and how it's relevant to you. So one slide only on what lattice QCD is. So it is a first principles numeric approach to the field theory. So take the Lagrangian that Matt was referring to of QCD, which is a well-defined concept, and attempt to evaluate correlation functions. So the idea is, take the path integral approach to quantum theories, where in the case of field theories, what that means is you take all possible configurations that the quark and gluon fields can have over space and time, and you average over them in a suitable way. And correlation functions are just that, with some function of the fields appearing here. And the lattice approach is to say, okay, so you can't evaluate these path integrals exactly, but instead take the fields and say they only exist on the sites of a grid. So a grid, you have a grid with some spacing A, and you have a box of some finite size. And once you do this, now your fields are taking values only at the various sites on this grid. Thank you. Now, to describe a particular configuration of a field, it's just a list of numbers. It's just a number for each site, right? Well, how strong the field is, if you like, at that site. And then the idea is, well, if you're supposed to just be averaging over all possible configurations that they could take, well, just Monte Carlo generate many, many, many configurations and average over them. Essentially, that's all that the approach is. And the sense in which it's approximate is, of course, that you introduce this grid spacing, which doesn't exist in the real world, and you introduce this maximum size of the little femto universe that you're considering. So in principle, if you repeat calculations with finer and finer grid spacing and larger boxes, then in those asymptotic limits, you approach the original correct theory of QCD. Now, a tedious practical problem is that this is computationally very intensive, and in practice, to do all but the simplest calculations, we make another fudge, which is we break into the Lagrangian. The Lagrangian features these parameters, which are the quark masses, which are set by some physics other than QCD, the Higgs theory, whatever it is. But they're free parameters. You can choose whatever number you want. So what we do is we break in and we take the light quark masses, which are extremely light in this universe, and we artificially tune them up to a higher value. So it's still QCD, it's just we've adjusted one external parameter. And in principle, over time, you improve this. You go lower and lower in the light quark masses until eventually you can afford to do calculations at the physical quark mass. But in practice, most calculations do this. So the relatively easy things to compute are what we call two-point correlation functions. So the idea here is you start with a vacuum, and then you act at some initial time with some operator, some quantum operator, and this is a combination of the quark and gluon fields of the theory, anything you like, and what you do is you construct that to have the quantum numbers of some hadron that you're interested in. So if you're interested in the pion with its pseudo-scalar quantum numbers, then psi bar gamma 5 psi is something that transforms like 0 minus plus. If you correlate that operator at initial time with, let's say, the same operator at a later time, relatively easy to show that this is just, well, you can see this is just a function of t, and the time dependence contains information about the spectrum of states with pseudo-scalar quantum numbers, and they appear like this, with a sum over all the possible QCD eigenstates with those quantum numbers. So in short term, the simple thing I can state is that what lattice QCD does for us for the purposes of this talk is it allows us to get access to this discrete spectrum of eigenstates of QCD in a finite box. Okay, and the question is that an interesting thing to know? What does that tell you about? Okay, yes, I have to press this. So let me give you an example of one part of a program of what we want to work towards that's particularly relevant to this audience. So we'd like to be able to predict and understand whether hybrid mesons exist within QCD and what their properties are. As an example, there are these experimental indications that there might be a 1 plus exotic above about 1.6 GeV. Now, I'll reiterate, Matt's point is exactly right. You need more than just to observe one such thing. You need the patterns. But let me just focus on one thing to be concrete. So, how do we learn in QCD whether such a state is present? Well, the point is that by looking at these correlation functions and constructing a large basis of these operators constructed out of quark and gluon fields, and here I'm giving you some details for how that's done, but you don't really need to care too much about this for this talk, you can get out a spectrum, a discrete spectrum of states. The only thing I want to say right here is what these operators look like is a quark field, an anti-quark field, and then a bunch of stuff in the middle, which is basically, you can think of as P waves and S waves and D waves, but also as gluonic stuff in there as well. But importantly, these operators so far are just a quark and an anti-quark, nothing more. So we do these calculations, and you've already seen the result. You've seen that it ends up looking like this, and Matt showed this. And this is a spectrum across spin parity and charge conjugation of, it's clearly a discrete spectrum of states extracted from a calculation in this way. And just to fill this out, this is in a world in which the light quarks are tuned up so that the pion, instead of weighing 140 MeV, weighs about 3 times that. It's not the real world, but it's not completely different from the real world. Okay, and Matt indicated a few interesting observations within this. If you want to know a little bit more about why we colour these states in orange and say that they're hybrids, you can read this paper for some explanation of why we come to that conclusion, even for states which have non-exotic quantum numbers. But of course, that last slide doesn't this spectrum that we're seeing here doesn't tally with something that we know, which is that the excited states in QCD, the excited hadrons, are not states of definite mass. They're not stable particles whose mass is one particular definite number. They're resonances who decay. And to go back to our case that we're looking at, this 1 plus guy, here's again the compass data, and the point is it's a resonance, it's a bump in a continuous distribution of hadron states. What you actually measure experimentally are not infinitely narrow spikes with nothing in between, but a continuous distribution of multi-hadron states. So the actual spectrum of QCD is continuous, not discrete. And what I just showed you was a discrete spectrum. So you'd be quite justified in saying, so lattice is doing something wrong. There's something missing, because there should be a continuum. In fact, any sufficiently accurate approach to QCD should reflect that. It should have a continuous spectrum of excited states. So how can that be achieved? Where, as I was showing you, the lattice QCD extracted spectrum is a discrete set. So there seems to be a discrepancy here. So let me give you a simple way of thinking about what's happening here by going back to ordinary non-relativistic quantum mechanics. No field theory, just quantum mechanics in one dimension, one space dimension. So suppose you've got two identical particles, spin 0, make it as simple as possible. that interact through some finite range potential. And it doesn't matter what the shape is. But here you go, here's one possibility. Then you know from your introductory quantum mechanics that you can have scattering solutions. And that is solutions of positive energy. And they have a wave function which outside the range of the potential looks just like a free particle modulated by this thing called the phase shift, which tells you all there is to know about scattering. So this contains all the information there is about scattering at various values of the momentum, but the momentum of these two particles that are scattering off each other is continuous. You can have any value from 0 up to infinity. So there's your continuous spectrum of states of this quantum system. And you know that this is a continuous spectrum. You know that generally any potential is going to have, for example, the Coulomb potential, can potentially have a bunch of negative energy bound states, but then a continuum of positive energy scattering solutions above E equals 0. So this is all just very obvious quantum mechanics. So this is just saying again that there should be a continuous spectrum of, say, meson-meson states in QCD. And yet I'm saying that the lattice calculations have a discrete spectrum. So what is that? What have we done in our approach to QCD that has moved us from a continuous to a discrete spectrum? And the answer is simple. We put it in a box. The moment we put the system in a box, we killed the continuum. And it's easy to see in this quantum mechanics example. So put walls, put a periodic boundary outside the range of the potential, like this. Now, of course, you've got boundary conditions here. You've got to have that the wave function and its derivative are continuous at these walls. And as soon as you do that to these scattering solutions, as soon as you apply these boundary conditions, you've now got a quantization condition on the momentum. You can't have just any momentum you like. You can only have the momenta which satisfy this expression. And if this is unfamiliar to you, just think about the case where there's no potential at all, then you know you've got to fit complete numbers of half wavelengths inside this box in order that it make any sense periodically. And that's what this is. But you see that when there is an interaction, when there is a potential, the spectrum of allowed momentum eigenstates that you can have depends upon the scattering as a function of momentum. So it depends upon the scattering phase shift. And it's this mapping that's useful. Now, of course, what this means is you don't have this. You don't have this continuum of p greater, of all possible p values. You only now have some discrete set. And what's more, that discrete set depends upon the volume, depends upon L, and it depends upon the scattering amplitude, the phase shift. So the idea then is that we should have a discrete spectrum, and what's more, we can run this thing backwards. If we compute the energy spectrum using lattice QCD, we can infer something about the scattering amplitude from it. So even though we calculate a discrete spectrum of states, we can still infer something about the continuous spectrum of scattering solutions for positive energy. And that's basically the idea. Now, I've shown you this for quantum mechanics. The field theory version is worked out. It's more complicated, but it's been done. So how does this work? I mean, I showed you Mac showed you also this spectrum of states we've extracted. So what was that? Should we be interpreting every level in there as some sort of resonance? Well, you can sort of illustrate this in the following way. So let me take the formalism that relates the elastic scattering phase shift to the discrete spectrum of states and supply a known phase shift. And the known phase shift I'm going to supply is one describing a narrow resonance coupled to, let's say, pi. If you do that, if you have an infinitely narrow resonance so that it actually doesn't couple to its decay channel at all, this is what you get. This is the energy spectrum against different box sizes. And each little black dot here is one energy level. And what you see is you get these dots which lie on the orange curves. The orange curves are just the energy of a pair of pions having an allowed amount of momentum in the box. So the pions could be at rest, in which case their energy is just the sum, just twice the pion mass. That's the horizontal line at the bottom. Or they could be moving back to back with the allowed unit of momentum, which is 2 pi divided by L. In which case they've got more energy. They've got twice the square root of m pi squared plus 2 pi over L squared. That's what this curve is. Of course, it's volume dependent because the allowed momentum is volume dependent, 2 pi over L. And this is higher momentum. And so you see you get an energy level for each pi-pi-like state, but then you get an extra one. Well, this is this infinitely narrow resonance that I've put in by hand. Now watch what happens if I turn up the coupling of the resonance to the decay channel. Watch what happens to the black points. They diverge away from these original curves. You get things like this and this. So the places where the levels originally crossed, the non-interacting levels crossed, you get an avoided level crossing. This is the same thing you get in perturbation theory in quantum mechanics, when you have two levels and then you turn on a perturbation that mixes the two. So the interpretation here is that in a finite volume, the eigenstates that you're getting, these guys, you can think of, roughly speaking, as being admixtures of a resonant-like state and a meson-meson-like state. Sort of what you're getting at. And this now, roughly speaking, explains what we were seeing before. What we were doing before was computing these correlation functions using operators which were just like a quark and an antiquark and maybe some glue in between. But that doesn't look much like a pair of pions, right? A pair of pions is 4 quarks distributed, flying around the whole volume of the box. So basically what our operators were doing before, they were only latching on to this bit, and they weren't latching on to this bit. And what we find is that when you do calculations that way, instead of getting 2 states here, which is what you should get, that's the correct answer, you get something that sort of sits in between the two in a slightly uncontrolled way, because it's really just latching on to what this wants to be. So what that tells you is what we were observing in those previous plots is an indication that there probably is a resonant state there, but we're not resolving its full properties. We're not resolving anything about how it decays, for example. And if you want to do better, what you have to do is use a basis of operators which goes beyond that one that I described before and adds in something that has strong overlap with, say, pi-pi-like states. That's relatively easy to do. This operator is something which overlaps with a pion, and so is this. So I just write the product of the two, and then that will have good overlap onto 2 pions. And when I do that, if I include such operators in the basis, and solve the problem again, I'll find more levels than I found before. And those levels can be turned into information about both the presence of a resonance and its decay properties. So just one sort of caveat along the way. We're very pleased, this plot gets showed a lot, but it's important to remember what it does show and what it doesn't show. What it doesn't show is precise estimates of the masses of resonances, for the reasons I just said. And it doesn't tell you anything directly about decay widths. What it does show is probably a reasonable guide to the distribution of states which are likely to be relatively narrow. Which is to say, if you do an experiment and you observe some, say, broad resonance that doesn't tally with anything on this slide, I wouldn't be surprised, because broad things probably don't get captured in here. We have to do something better. Also, to learn anything about how these states decay, we have to do more, and that's where the state of the art is now. So let me give you an example of how this finite volume business can work in practice. So predictably, I'm going to start with the simplest possible example. So consider the row resonance in pi-pi scattering, which Matt very kindly also, without any collusion, showed this example. So here it is. And of course, what you do is you do an angular extraction. You extract the different YLM moments, and you get a scattering amplitude in the P wave. And then you hopefully know that in elastic scattering, you can transform from the scattering amplitude to this phase shift as a function of energy. And this is the phase shift of the rho, and this is the absolute classic observation of a narrow resonance, right? A phase shift which starts at 0, goes up through 90, and saturates somewhere near 180. So you can argue QCD, an accurate QCD calculation should be able to duplicate this kind of behavior. If a QCD calculation says, I can tell you something about the rho, you should be saying, yeah, can it do this? Can it show me this? So that I know there really is a resonant rho decaying into pi pi. So I've sort of sketched out how this works. Do your lattice QCD calculation and compute this discrete spectrum in a box. So that's what's shown here. 3 different boxes, 16 cubed, 20 cubed, 24 cubed. Energy spectrum, each of these little black dots. We see there's only 1 point here, only 1 here, 2 here. But this one's above kk bar threshold, so it's not very interesting. Okay, so that's not great, 3 points. But it turns out you get more information if you also consider frames which are moving with respect to the box. Because in those frames, the box gets length contracted, and so the quantization condition on the momentum is actually different, because effectively the box length in the direction of motion is different. So that's what these guys are. Different boosts, if you like, and you see there's a bunch of other points here. And the details don't matter, except that this is a calculation that can be done and has been done. Again, in this slightly fake heavy quark world, but nevertheless, it's been done. And then the approach is, for each of those energy levels, you can feed it through a formula a bit like the one I showed you, but slightly more complicated, and the output is the phase shift at that energy. So for each energy point, through a little bit of magic, not magic, but through a little bit of solving a hideous equation, I get the phase shift at that energy. And then I can plot that phase shift, now a discrete phase shift as a function of energy, and it looks like this. Now ignore the silly units here, this is just lattice units. The point is each of those points on the previous slide becomes one of these points for the P-wave phase shift as a function of energy. And without any doubt, there is a resonant-like behavior there. There definitely is. So this is telling you there's a rho about here, and the slope is telling you about the decay width. We've actually done this calculation again using lighter quark masses. So in a world where the pion weighs about 250 MeV, and that gives you, the blue points here are just what you saw on the previous slide with a bright Wigner curve fitted through them. The red points are a lighter pion mass, redoing the calculation. And you see what happens is it moves down in mass, great, the quarks are lighter, the rho should be lighter, and it gets a much larger slope, which means it gets a larger width. Which makes sense. There's more phase space to decay into 2 much lighter pions than there was into 2 much heavier pions. So the width goes up. And if you take this a bit further, as my collaborator Raoul did, and build an effective field theory of this, you can extrapolate to what will happen at the physical pion mass, and it's bang on, right? You get exactly the right mass and width for the rho. So this looks very promising. It looks like you've got a technique in lattice QCD, which is a first principles approach to studying at least elastic resonances, albeit in this case the simplest possible elastic. Just to foreshadow something that's going to come later, if we want to be a little bit more precise about what we mean by the mass and width of the rho, or really the mass and width of any hadronic resonance, one thing we can do is actually think of the scattering amplitude as being a function of complex energy. Take the energy to be a complex variable, and then a simple resonance corresponds to a pole-like singularity somewhere off the real axis. This is the real energy axis. You go some way off, you'll find there's a pole-like singularity. And you can argue that's what the rho is. That's how you know there's a rho, you find a pole-like singularity there. And here it's pretty straightforward to do that. Okay, so that's fine for elastic scattering, but of course we've got to face facts. Most of the resonances we're going to be interested in are not elastic resonances. They decay to more than one final state. So going back to our example case, the 1 minus plus resonance, yeah, okay, we've already seen that it can decay to rho pi, but, and again, Matt showed this, it's almost like he hacked into my computer.
Uncanny.
It also decays, apparently, to pi eta prime. That's a decay channel of this state. So it's not an elastic resonance. It's a coupled channel resonance. It appears in multiple channels. And so you have to find a way to handle that. Because it appears in multiple channels, it can't just be described by a phase shift. There has to be a T matrix, an S matrix, a matrix of scattering amplitudes. So the question is, how do you deal with those in your lattice world, in your finite volume world, I should say? So this has only very recently been started to be studied. And this is what it looks like. So this is sort of slightly complicated, but you don't need to know the details of this except to say that this is the condition that determines the finite volume spectrum. And what has it got in it? This is the scattering matrix. So this is all the information there is about scattering in whatever channels are open as a function of energy. This is the phase space. Okay, that's straightforward. And these are some known functions. These are kinematic functions. And the idea is if you have T as a function of E, if you have the scattering matrix as a function of energy, you evaluate this expression. It's just some complicated function of E. You find all of its zeros, and that's the finite volume spectrum. Fine. But what you do is you calculate the finite volume spectrum, and you try to work backwards to what T of E is. Just like before, we calculated the E's and we worked backwards to delta of E. Well, the problem here is this is one equation. It's the determinant of a matrix. One equation in, well, multiple unknowns. This is a matrix T of E. So even in the two-channel case, it's relatively easy to show that to describe scattering in two channels, you need three real numbers. So this is one equation in three unknowns for the two-channel case, and nobody can solve that. So what do you do? Well, the approach we've taken is say, okay, well, we can't do this for one energy level, but we're not going to have just one energy level. We're going to have a load of them. Do lots of different volumes, get multiple excited states. Why don't we use all that information at once? By parameterizing T as a function of E, in terms of some relatively small number of energy-independent parameters, and then by varying those parameters, ask ourselves, what finite volume spectrum does that model of scattering predict, and compare that to the one we calculated in the lattice calculation. And then adjust the parameters within the parameterization until the two agree with each other. And at that point, you've got T as a function of E. Max as well constrained by that lattice data as you can. I'll skip this bit. So just to show a cartoon of that, here is the black points are calculated lattice finite volume levels, and the orange dots correspond to some parameterization that has, in this case, three free parameters, and we just allow those. We allow min-wee to minimize in that space of parameters, starting from some random position. And what's shown in the top right is a way of showing what the scattering amplitude, scattering matrix behaves like. So we start from some random position in that parameter space, and we minimize the chi-squared by, insisting that the spectrum be described. So this is pretty straightforward. It's a pretty common approach. Okay. So actually, the first place that this was considered was in the coupled channel scattering of pi k and eta k. And I could talk about that for plenty of time, but I won't. This was the first place it was ever done. It's very interesting, but it doesn't show the full glory of coupled channel scattering because it turns out QCD doesn't want these two channels to be strongly coupled to each other. Right? It turns out, in the end, that there's a very weak coupling between the two channels. So it's not that interesting. It is interesting, but it's not as interesting as it could be. So I'm going to skip that and go to our most recent result, which is where it gets really interesting, which is two channels that definitely are strongly coupled. So experimentally, in pi eta kk bar, it's long been known that there's this enhancement called the A0 980. So pi eta threshold is down here, and then at a slightly higher energy is kk bar threshold, and there's something which appears right at kk bar threshold that's called the A0 980. And here are some amplitude extractions of essentially the cross-section. You can think of this as the cross-section for pi eta to scatter to pi eta. You can't measure that directly, but you can sort of infer it from more complicated processes. And these are various different model approaches to extracting that. And this is energy with respect to kk bar threshold. And you see there's very clearly a big bumpy thing at kk bar threshold. There's something strong there. It's clearly not a symmetric Breit-Wigner-like bump. It's got something cuspy about it. It's not a standard-looking resonance. Furthermore, these amplitude analyses all pretty much conclude that that there is a resonance there and that its coupling to kk bar is about as strong as its coupling to pi eta. So I present this as an illustration of somewhere where in experiment you have a strongly coupled channel system. You have two channels which are strongly coupled together and a resonance is present. So this is a challenge for the QCD calculations. Right? Can we duplicate such an observation? Can we see something comparable to this? So we did this. So here are the finite volume spectra again, this time for the quantum numbers that look like a pi eta or a kk bar. And basically, without focusing too much on the details, what you want to see is there's lots of little black dots here. Right? These are the end result of an explicit lattice QCD calculation. Here they are. And of course, each of those points is part of our constraint on the scattering T matrix, which is going to be a two-channel T matrix, pi eta and kk bar. And we're going to parameterize that, try to describe all of these points. So it's going to be pretty well constrained, right? Because these points cover the whole region of energy we're interested in. This is pi eta prime threshold. So that's where we're going to stop, basically. But the whole region below there is filled up with points, and there's lots and lots of them. And we're going to parameterize the T matrix with only a few free parameters, 4, 5, 6 at most. Whereas there are 40-something points there doing the constraining. So we did that, and this is what you get. So here I'm plotting, this is the T matrix, pi eta to pi eta to pi eta, pi eta to kk bar, and kk bar to kk bar. And what I'm showing you here is essentially the magnitudes of the elements of that matrix. This particular combination is pretty much proportional to the scattering cross-section. So what do you see? Pi eta to pi eta is in red. This is kk bar threshold, because remember we're working with these artificially heavy quark masses. So it's not at the 980, it would be experimentally. It's clearly something happens there. And then pi eta to kk bar turns on very rapidly at threshold, and kk bar to kk bar turns on very rapidly at threshold. The bands here correspond to propagating that Monte Carlo error all the way through the calculation. So there's clearly something happening here. There's clearly something strong happening at threshold, and there's clearly strong coupling between the two channels. So it looks like a first principles QCD calculation is showing us some of the properties that we believe QCD should have on the basis of experiments we've done. Stop me when I'm running.
What was the braille on the bottom of the plot?
Ah, good question. What are the totally invisible dots down here that apparently Matt can see? That was all those energy levels from the previous plot, now just plotted horizontally. And the point is to show you that they appear everywhere in this energy region. So there is constraint on these curves everywhere. It's not the case that there's a few points down here, a few points up here, and we're doing a totally unjustified interpolation between the two. There's constraint everywhere. That's what that's designed to show.
These results are independent of the size of the cube.
No.
Yeah.
No,
So
not
because you put M, but not
this.
L.
This is independent of the size of the box. The energy spectra definitely aren't independent of the size of the box. They're extremely dependent on the size of the box, and that's the whole physics we're using, the fact that they are extremely dependent on the size of the box, but in a known way, in a way which is determined by that determinant condition that I wrote earlier. So, first thing to notice is that does look quite a bit like what we were seeing in experiment, which is already kind of pleasing, but we'd like to do a bit better and understand what's happening here.
So at the threshold there, where you have the very rapidly changing curves, you have some gaps there, right? So are you still be able to constrain it enough? Yeah, you have a gap in there.
Well, look, you could, if you were very skeptical, you could say yes. You could have arbitrarily strong behavior in here, but physics doesn't behave like that, right? This is a scale of 10 MeV. We don't see that. We generally don't see that kind of physics. How would you ultimately test that? You could do more volumes and you would fill this out eventually. So there's clearly some sort of strong cusp-like behavior here. There's these very rapid turn-on of the kk bar amplitudes. Now, you can always have a cusp when a threshold opens. That can always happen. It doesn't mean there's anything resonant going on. But this is a really strong cusp. And these amplitudes turning on essentially as fast as they're allowed to strongly suggest that something is resonating here. There's some sort of resonant behavior in the region of the kk bar threshold. And I think even if we didn't know that the A0980 exists experimentally, we would infer from this that something is happening. But how do you do any better than making that sort of vague statement that there's probably a resonance nearby? Well, the point is you've got a parameterization of t as a function of e. I haven't told you what it is, because I could, but I haven't told you what it is. But you've got it. It had some free parameters in it, but you fixed those free parameters by describing the finite volume spectrum. From that point onwards, well, there's nothing stopping you now taking the energy variable and considering it to be complex and going off the real axis and asking, does this parameterization have any poles in the complex energy plane, pole singularities? If it does, our conventional interpretation is that they are resonances. You find one, it's the real part of its energy tells you the mass, and the imaginary part of its energy tells you the width. You can just do that. Go and look. This is the sort of idea, right? The T matrix should have these factorized poles. So this is a pole singularity. And these guys are the couplings of this resonance to the various channels, to pi eta and to kk bar. And it's complicated because there are multiple unphysical sheets. I don't know how many of you have heard of this before, but the point is every time a new threshold opens, you get a square root branch cut because the momentum is the square root of the energy. So it turns out you get these multiple Riemann sheets, and you can ask which pole is the Riemann sheet on. Let's not worry about that for this talk. Let's just ask, is there a pole somewhere off the real axis? And there is. So here's the real energy axis. Here's the imaginary off this kk bar threshold, and indeed we find a pole here. Now you might say, well, what are all these various red points here? Well, one criticism you should have leveled at me is you chose the parameter, you being me, chose the parameterization of T of E. Why should I believe you? You just cooked something up, right? Yes, I did. I just cooked something up. But I cooked up loads and loads and loads of different parameterizations and used them all, tried them all. And every one that was capable of describing the finite volume spectrum with a reasonable chi-squared gave me basically the same amplitude plots you saw previously. And what's more, when I examine each one to see does it have a pole, they all do, and they're all in the same place. And the point is, they had to get that sharp feature at threshold, there has to be a pole. and it's close to the real axis, relatively speaking. So there is indeed a pole there, and the point is you can get out of that there is a resonance there. And just in case you were curious, you would guess that it must be the case that that resonance is coupled to both channels, right, to pi eta and to kk bar. And indeed it is. You can also extract those couplings, right, by just going to the pole and asking what is the residue of the pole. You do that, and this is what you find. You find that the couplings, of course, can be complex in general, but they're close to real, and you find that they're of similar magnitudes. The coupling to pi eta and the coupling to kk bar are of pretty similar magnitudes, which is very pleasing because that seemed to be what was happening experimentally too. So this is very promising because this now seems to suggest, okay, so the lattice QCD approach, finite volume approach, potentially is useful for studying coupled channel resonances, which is what all the interesting resonances are. Okay? But there has to be a downer, right? Nothing, you don't get to be happy for long. You go back to our example case, the pi 1 minus plus, and you remember that initially I tried to sell you this bill of goods that it decayed into rho pi, right? And it does decay into rho pi, but the pi doesn't hang around for the rho doesn't hang around for very long. It decays into 2 pions. So actually, what the 1 minus plus is really decaying into is 3 pions. Just sort of, we believe it's sort of dominantly doing it through a rho isobar. So really, most of the resonances we're interested in don't decay into meson-meson pairs, but decay into higher final states, higher multiplicity final states. And I will be honest, this is where the cutting edge of formalism lies. The approach to turn the finite volume spectrum that we compute in lattice calculations into 3-body amplitudes is right at the cutting edge. That's the limit of what we know. And that's being worked on actively as we speak. And optimistically, I think you might see within a year or so the first calculations of three particle amplitudes in not this kind of case, but in things like high isospin 3, for example. But this has got to be solved before we can really address high-lying resonances like these. We've got to work out this formalism and show that we can carry on our success. Okay. Well, what else? This is a GlueX talk. So what's unique about GlueX? Well, it's the photon beam. The photon beam is the novel feature. So part of the idea is you're trying to make this pi 1 in perhaps some process like this, photoproduction of say, charge exchange photoproduction, for example. And now you can ask, well, can lattice calculations offer anything here? Is there any chance that you can say from first principles QCD something useful about this process? Well, in order to understand this process, its whole rate is controlled by sort of how big is this vertex? How big is the coupling photon-pion exotic 1 minus plus? Right? And that we just don't know. We've long suspected that it might be large, but we don't know. We haven't done a first principles QCD calculation. So can that be studied within lattice QCD? Well, the good news is yes. And the first calculation of a simpler case has appeared. Excuse me. And the principal author of this is sitting in the room currently. That's Raul Briceño. And what this case is gamma pi goes to 2 pions. So it's a relatively simple case where the 2 pions are in a p wave, and so you expect the rho to appear. You expect this to be basically on-shell or off-shell photon is absorbed by a pion and turns into a rho. But of course, we don't put the pion in. This is a first principles QCD calculation. The only dynamics present is quark and gluon interactions. And we do some calculations in a finite volume. We apply a certain formalism. And what we get is the amplitude as a function of pi invariant mass and photon virtuality. So this, for comparison, this is pi elastic scattering, which is basically what I showed you before as a phase shift, just turned into the amplitude. And yeah, there's a bump in there, right? That's the rho. So the question is, does the row appear in the photon amplitude too? And sure it does. Here it is. And what's more, as you tune the virtuality of the photon, you find that the intensity of this process goes down as you increase the virtuality of the photon. Well, that's nothing more than what is the rho to pi gamma transition form factor. As you make the photon more virtual, the form factor falls, just like proton form factors or pion form factors. And indeed, you can rigorously extract something which you can identify as the form factor. But the point is, you can imagine extending this to more complicated cases where it provides you some information about the photoproduction process at GlueX. Okay, I'm coming to a close. I've shown you examples in the light meson spectrum, but everything I've shown you is in principle applicable to baryon physics too. Right? Rather than studying pi-pi elastic scattering, you could study pi-n elastic scattering and hope to see the delta baryon as an analog of the rho. And that can be done. It hasn't been done yet, but it can be done. It's also, again, to refer to something that Matt was showing, you've got these mysterious new states in charm and charmonium, the X, Y, and Z states, are coming out of high precision, high statistics data. These techniques are going to be the way to understand those states eventually. What I want to emphasize is that everything I've shown you is progress in the last 5 or so years. This has been incredibly rapid progress, moving from not really being able to say anything about the excited hadron spectrum in first principles QCD to now being able to study coupled channel resonances and the coupling of resonances to external currents. So we've done that in 5 years. Now, you could argue, well, that was the low-hanging fruit. You've got to get a bigger ladder now. It's going to be a bit harder. Well, maybe, but we'll see. We're hopeful that we're going to be able to do much more along the lines of what I've shown you. And just to show you a cast of characters, the numerical calculations I've shown were all done by the Hadron Spectrum Collaboration, which has its sort of center of gravity here at Jefferson Lab, but also has external entities across the Atlantic who are mostly focused on charm and charmonium calculations. And here's the complete list of publications since we came into existence in 2009 or so. Thank you.
All right. Thanks, Joe. Anybody have any questions?
You were talking about, going from the spectrum that you calculated with 0 width resonances to, resonances that have a width. I understood you said that, you kind of calculating kind of the average or pulling out one of those spectrum. Am I to understand from that one should multiply the number of states by 2?
No. So let's go back to this. This is the rho in pi-pi, which was really the illustrative case I was giving. So let's focus on, for example, this panel. You see that there are 2 states here? This is the 2 states I was talking about in terms of interpreting potentially as an admixture of a resonance and a pi-pi state. Those 2 points there turn into 2 points on this phase shift curve. But there is only one resonance here. So no, there aren't 2 resonances, there's just one resonance. So what happened with this spectrum before we included the operators that looked like 2 pions? Well, what happened is here, instead of seeing 2 levels, we saw one level sort of sitting in the middle. And that's how we knew that, you could argue, that's how we knew there was going to be a narrow rho, but we couldn't resolve any of its properties in detail, its decay physics, until we got the correct spectrum, which is this one. So no, it doesn't mean that there's necessarily each of those levels should be multiplied to make multiple resonances. What it probably means is that on that basic plot, each box probably corresponds to one narrow resonance. But could there be broader states that are being missed? Yeah, absolutely. And are those resonances at exactly the correct mass value? No, they could easily move within the width of a state or even more. Does that answer the question?
It seems like there's some commonality between what you're doing in last QCD and what we do in experiment, in that you measure phase shifts, we may measure things, phase differences or something like that. But at the end of we're trying to fit data and find out how many poles are there and what. So can you say anything about kind of the common technology that applies in both cases and the opportunities to build off one another and
so I think things? That's exactly right. I think right now we've been doing the simplest cases, and in particular we've mostly been considering states whose poles lie very close to the real axis, which is to say narrow resonances. And roughly speaking, you sort of can't get the parameterizations of the amplitudes wrong, right? You have to really blunder to get something that doesn't work. Almost everything works because they're so close to the real axis. But it's clearly going to get much more complicated when we go to, for example, multi-body final states. And what I envisage happening in the future is with something like JPAC, is you've got people who are getting to be experts at constructing these amplitudes that have good analytic properties and respect unitarity wherever possible. You will be using the same amplitudes to describe the finite volume lattice spectrum that you're using to describe the data. And in that sense, you have as close to a like-for-like comparison between QCD and experiment as at least currently you can envisage. But definitely there's going to need to be a much higher level of integration of assets.
That might be a very dumb question, so please be forgiven. When you are combining in slide 15, just so you understand me completely. So when you are using the resonance and a possible channel as a basis, the possible channels, I guess you get them from physics. That's what limits you, and you use minimum possible to make the matrix smaller. For the resonances, you also assume the minimum possible.
But I'm not. This is just a cartoon. This is just a cartoon of what's happening. In terms of the question is when you're writing down your basis of operators, really your question is how do you know when to stop, right? Well, with the psi bar something psi, we include increasingly complicated stuff in between the psi bar and the psi. And what you observe is that eventually you add more and more and more operators, the spectrum doesn't change. So you just quit, right? There's no need to do any more. In terms of what meson-meson-like operators do you include, well, it's essentially kinematics that tells you that. You only need to include those things which are close to being kinematically open. Okay, so, well, this was a cartoon, right? But pi, for example, in the pi eta case, go to that finite volume spectrum. What operators did I include when I was extracting these spectra? Well, pi eta, that's its threshold, kk bar, and here's pi eta prime. So what did I include? I included things that look like pi eta, kk bar, and pi eta prime. I didn't include things that look like, using something ridiculous, j psi pi, because the lowest such level is way, way, way up here. So the role that it can have in determining the spectrum down here is irrelevant. So essentially the masses of hadrons and kinematics tells you what your operator basis needs to be at a minimum. Yeah.
So what do you see your collaboration tackling over the next couple of years?
So without giving too much away, walls have ears.
This is recorded.
The whole world's watching.
This is all public. I mean, I can suggest obvious things, right? So So what you've seen, I've shown you pi k, right? I just flashed that up. And here's pi eta kk bar, in which a low-lying scalar resonance appears. So you might reasonably have said, yeah, but hang on, isn't the really interesting low-lying scalar resonance the sigma in pi pi? This is this big, broad thing that appears in pi pi isospin 0. Well, someone will look at that at some point, right? And then there's the F0 980, which is the isospin 0 analog of the A0 980, coupled pi pi kk bar. Someone's going to look at that. So the scalar stuff is going to get done on a short time scale. You can imagine that there's going to be a bit more of this photon coupling to stuff business, because that's interesting. And then once the formalism is in place to some extent, these three-body final states are going to have to be looked at in quite a lot of detail. That's going to be a lot of work, 3 pions, for example. So you can start to see that this is already going to start to fill up multiple years. And just to emphasize, this room contains a fraction of the GlueX collaboration membership, right? A fraction. This is the entire Hadron Spectrum collaboration membership, including people like me who are faculty members and thus actually useless in any practical sense, right? Not actually get anything done. So we're really, these efforts are big efforts, but with a small number of people. So people always think of lattice QCD as being computer time limited, right? It's how powerful the computer is that limits what you can do. Well, computer time is necessary, but not sufficient. You also need warm bodies and firing brains to do this stuff, because it's gotten quite sophisticated. So really what we need is more manpower. We really need more personnel, more people to think thoughts and do things. So in terms of what we get done, in terms of extending to things that are maybe slightly outside of the mainstream of GlueX interest, which is things like baryon spectroscopy, which of course is extremely important in class, for example, that's on the back burner at the moment because we just don't have enough people to do it. And the amount of stuff going on in CHARM is not as much as we would like, even though lots of the experimental interest is in these X, Ys, and Zs. Okay, so that's my rant about make sure to say nice things to the funding bodies about us.
One last question, then we'll go coffee break.
From your spectrum, you're saying you wouldn't be surprised if we found something that was broad, that didn't fall into your category of states. Can you be more quantitative about what broad means there?
No.
Because some of those states we might expect to be broad already.
Yeah. So there's one sort of fudge in here.
If it's not there, it's broad.
Yeah.
There's one slight fudge in here, right? Because I'm saying that each of these states probably corresponds to a relatively narrow resonance, right? That's what I said repeatedly. But probably corresponds to a relatively narrow resonance at this pion mass. The widths could go up, and in some places they're going to. Like that the 1 plus plus is much. The isovector 1 plus plus is quite broad, so something's happening to that probably. So can I be more quantitative? No, not really. Not without actually doing the right thing, which is what the whole second half of the talk was about, right? Is fessing up to what the limitations of this is. And we need, sort of the first 3 pion calculations will tell us something, I think, a lot more about interesting things like 1 plus plus and 2 plus plus. But yeah, no, afraid not.
All right. Thank you, Joe. Let's take a 20-minute break and come back at 3:55.
Okay. Office outside, we assume?
Oh yeah, refreshments outside.
Thank you.
Yeah.